Well, hello everyone. My name is Jac van Egmond. I'm the founder of mvAERO, a small design and engineering company located in Delft, the Netherlands. I've been using XFlow for the past 6 years, and today I thought I'd share with you two examples of how my findings in XFlow related to a wind tunnel test that I performed. The first example will be on a single element airfoil section, just a simple wing, and the second will be on a full-size car, the so-called eco runner, a very fuel-efficient car where aerodynamics is very important. Sorry about that. So we go right into it. First, a little bit about mvAERO. I started this company with a main goal, or a dream rather, to work on the most aerodynamically advanced projects in the world. For example, you see the Flying V, which gets a lot of attention these days. It's a radically new concept developed by the TU Delft, which I'm also a part of. And on the right, you see an electric vertical takeoff and landing craft using 8 rotors, which I designed, which is, to me, are really interesting projects, and it's really XFlow that allows me to contribute to these projects. So I'd like to thank them for it. So we'll go right into the first example now. I'm working very closely with several academic groups, and the same question often arises, like how do your results out of XFlow relate to our wind tunnel test or to the wind tunnel test? And this is actually a picture I took in 2015, where I tested the single element airflow section at wind tunnel at the TU Delft. And this is the result under a ultraviolet light. So I'll guide you through the flow pattern a little bit. If we start at the center section, the flow direction is from the bottom upward. And at the nose, we have laminar flow over the body up until maybe 15–20% chord. And where all this oil accumulates, and that's where the laminar separation bubble is. After the laminar separation bubble, the boundary layer becomes turbulent, and you can see it pushes away the oil more and more until we hit trailing edge separation, where the oil is moved sideways, which is really, it's the picture that is rotated. This is really due to gravity, so it's really the air flowing down. This flow pattern in the center section is very much as we expected it to be. We have laminar flow, we have a laminar separation bubble, we have turbulent flow and trailing edge separation. This is what we were looking for. We weren't looking for that you can see at the wall. We see a non-homogeneous flow pattern, and these two walls on the side, really the sides of the wind tunnel, have a tremendous and dominating effect over the airflow, resulting into so-called wall-induced stall cells. So we have really an effect here that's inherent to the wind tunnel that we don't even want to measure. We are not interested in that at all. So one of my very first projects with XFlow was to figure out whether we could simulate these wall-induced stall effects in XFlow to get some idea of their magnitude. So this is a movie I made about that, and one of the things you can see if we pause it here at a very early stage, then you can see the flow starts out to be quite homogeneous along the span, but as time moves on, these wall effects start to creep in from the sides, and we get a very homogeneous flow along the span. So great, XFlow can replicate the wall effect, and we're able to get some sense of the magnitude, but XFlow can do more than that, which brings me to the first main advantage of XFlow, because XFlow can just turn off this effect. It can just impose a zero friction condition at the wind tunnel wall so that these wall effects are just non-existent. And on the left, you can see one of the wind tunnel tests, and you can see the same section with the wall effect on in XFlow in the center, and on the right, you can see that the wall effect is turned off. And one of the not so easy to see but important aspects is that even the flow in the center section is a little bit different because the flow is now homogeneous. So that's really the first advantage of XFlow that I wanted to point out. And now we're moving on to the second example, and we're going to talk a little bit about this car on the right, which is built by the EcoRunner Team Delft, which is a group of students, and they compete with another group of students like the one on the left, but hundreds of others of groups around the world for the prize of designing and building the world's most fuel efficient car. And last summer we had a chance to perform a full-scale wind tunnel test with this little car at the DNW wind tunnel in the Netherlands. So this is me applying the final touches on some vortex generators. And but before the wind tunnel test, obviously we used XFlow extensively to iterate our way towards a more efficient design. One of the things you would look out for is maybe you see this onset of turbulence here because of the interaction of the wheel and the body. Also, there's quite a bit of trailing edge separation here, which is one thing, one major drag source. And it's these kind of images that would lead us to a better and better design incrementally. Our projected drag coefficient out of CFD was about 0.19, which is okay, it's pretty good. An extremely good streamlined body would maybe be 0.1. A car on the highway might be something like 0.4. So now for the wind tunnel test, we measured a staggering drag coefficient of 0.33. So that's like 60% higher than what we were measuring in CFD. That's a huge difference. And we were quite stunned by that. We were so stunned, in fact, that I decided to investigate what was going on, because I didn't believe that this car had a drag coefficient that high. It didn't really seem reasonable. You might expect it to be a little bit higher than the CFD result, but not that drastically. One of the first observations you can make from this picture is that the car itself is quite large compared to the cross-section of the wind tunnel. So that's observation number one. And then observation number two is really asking the question, how exactly is force measured in this wind tunnel? And the answer to that is actually rather interesting. It's the forces are measured on a balance that lies outside of the wind tunnel. And to attach the car to that balance, it needs to first be attached to a flat plate. And which you can see here, and the flat plate is rather big. So it's the car that's fixed to a flat plate, which is fixed to a force measurement apparatus. So that means that any forces on the plate are also included in your force measurement. I mean, this is obvious to everyone working in the wind tunnel as well, because they subtract, or they also do a run without the car, with just the flat plate, and they subtract the two of them. But they don't account for the interactions, the intricate interactions that happen between the car and the flat plate, which turn out to be very important. So how to proceed, how to solve this mystery? Well, in XFlow, you have the freedom to create basically any setup that you want, which includes a wind tunnel setup like the full-scale test. So we had a very similar cross-section, we had a very similar flat plate attached to the eco-runner, and so we have a similar blockage ratio, and we ran our simulation again. One of the interesting, most striking things that happened from this simulation was that to look at the airspeed, because the airspeed measured in the wind tunnel is measured up right here, and then that airspeed, that dynamic pressure, is used to quantify the effect on the drag, or is used to quantify the drag coefficient, which is measured, so it's measured in front of the car. But the actual effect on the drag, that's the airspeed that's increased because of the blockage ratio. Just because the car is there, the airspeed, because of mass flow, constant mass flow idea, the velocity must increase locally over the car. And that has an effect on drag. So we measure the airspeed here to quantify our drag coefficient, but you might even be better off measuring it here. It's actually quite hard to figure out where exactly to measure it, but this is not necessarily the correct place for it. So that's one thing. And then the other observation is that the flow over the flat plate is very different. So the drag on the flat plate is very different if the car is there or the car is not there. For example, because of that blockage ratio alone, you can see that the velocity here at this point on the flat plate is about 8 meters a second. Here it's about 10 meters a second. Well, it's a huge difference in terms of drag, especially if you're taking coefficients based on some determined airspeed. But it's not just that, it's also the interaction also causes the flow phenomena to be different. So there's actually a little bit of separation here on the flat plate, which is non-existent in the condition where the car is not present. Well, if we grab all this together into one results picture, then what we measured in the wind tunnel for the body and plate was a drag coefficient of 0.39. When we measured just the plate, we had 0.06. So we extract from that the drag on the body supposedly is 0.33. Well, if we do the same thing in CFD, we have 0.35 for the body and plate and 0.05 for just the plate. And we could say, well, our drag on the body is 0.3, but we'd be completely wrong, because for a very similar CFD simulation, without all these wall effects and without these constrictions, we measured for the exact same car a drag coefficient of 0.19. So we can conclude that due to the wind wall and plate effects, the drag is overestimated by about 60%, which is, I mean, that's just tremendous. And using XFlow, we can account for this increment in drag for about 80%. And what I mean by that is that about 80% of the increase in drag of 0.33 based on these two numbers compared to our initial 0.19 can be attributed to these wall effects and the plate effects. We still have a little bit higher drag than in the wind tunnel compared to our 3D model, and that's because the real car, you can see the tape here and wiper blades here, is a little bit has a little bit more drag. The second cause is that XFlow just does not have enough computational sources to solve the boundary layer in microscopic detail. So we go into a conclusion, and that both the wind tunnel and XFlow have their limitations. The wind tunnel does simulate these microscopic aerodynamic effects very accurately. However, we've seen that it runs quickly into wall interference effects when we increase skill. XFlow, on the other hand, does not have any wall interference effects. At least you can give it wall interference effects, but it doesn't necessarily have them. However, it's limited by computational power to assess these microscopic aerodynamic properties in the boundary layer. It's interesting to look at the solutions for these problems, because for the wind tunnel, the solution is to increase in size, and given that these wind tunnels are already the size of buildings, it's not very likely to change in the future. But the solution for XFlow is to simply increase the computational power, and that's almost a fact of life that it will increase over time. So I'd like to end my presentation by saying that the future for XFlow therefore looks much brighter than the future for wind tunnel. And this is actually the latest iteration of the EcoRunner car that we simulated, where we've eliminated a lot of the drag sources, and you can see in quite a high detail that these boundary layers are accounted for. You can see the turbulence flow, you can see a little separation cells, you can see quite a bit of turbulence up top. So I therefore like to conclude this talk and thank you all for listening. And if you have any questions, please send me an email or let me know in the chat. Thank you.